Now, if we talk about the MOSFET, we definitely need to look at the band diagram, right? I think you are pretty familiar with the band diagram, right? So this is the gate. So it only has one Fermi level. We're talking about metal gates, right? And this is the oxide. So it has a wide band gap. And then this is the silicon. And we already know that this is the conduction band edge. This is the valence band edge. And the middle of it is the mid gap. Right? This is a spelling. It should be mid gap. Mid gap EI. And then you also have Fermi level. What type of doping is this in this substrate? N type or P type based on the band diagram I draw?
P type.
P type, very good, because it's close to the valence band. Very good. In case some of you got lost, let me remind you what we are doing here. We have a transistor, N plus, P, that's why it's P type. This is the gate. I'm doing a cut here vertically, A dash, A dash. Okay, I'm doing this cut. And I'm looking at the band diagram. Okay, in particular, we have a concept called surface potential. It means this is the this is at 0, right? So we talk about the potential at this point. But it's just, how do we calculate this? Calculate as the conduction band potential here, and then the infinity. In this case, it is 0 because they are the same. Right. Well, our goal is to bend the surface potential so we can turn on the transistor. Okay, but we will talk about this later. Now, as I show you again, we're doing a cut. This is the source, this is the gate, this is the drain, and this is the P-type substrate, right? So at flat band, how would this look like? I will just draw it. This is so-called flat band. The band is flat, okay? So what type of carrier do I have here? You told me P-type, right? But can you tell me what type of carrier do I have here? Electron or hole?
Holes.
Holes, right? So if you try to look at the structure, then basically you're saying this, I have a lot of electron, right? And then I have hole here. Can I conduct any current in this condition? No, right? Because you are just having a back-to-back PN diode. Right? Because you have N, P, N. Right? So no current. Okay. Let's look at so-called accumulation. Accumulation is Vg smaller than Vt, or let's just say Vg is 0. Okay, not smaller than Vt, but very negative. If you remember, how do you do this band diagram? You make the Vg equal negative, then you will get something like this. Okay, if you don't know how to draw it, because this is not device class, but I want you to appreciate what's going on here. What do I have here? Electron or hole at the surface? You see the Fermi level is below the valence band. Do I have electron or hole? Last time you already told me that when the Fermi level is close to the conduction band is electron, when it's close to the valence band is hole. So do we have electron or hole here?
Holes.
Thank you. A lot of holes. Right. So still, can we conduct any current? No, right? Because it's still NPN. Okay, good. Then how about I go to the another direction? I make the VG larger, but it's still smaller than VTH. I make it larger, but still smaller than VTH. Then what will happen? I might have something like this. Okay, not a good drawing, but in this, at the surface, the Fermi level is in the gap. Okay, it's not close to EF. Let's say it's not close to neither EC or EV. So in this case, I don't have carrier, electron and hole. I don't have electron and hole. We call it depletion. It's depleter of carriers. Okay. So do we have currents if we deplete it with carrier?
No current.
Again, no, right? Because no carrier, no water molecule. How can I have water current?
Also, because you said VG is less than VTH.
Yeah, but they are correspond to each other. The reason VTH, we call it VTH, is because after VTH or just at VTH, the Fermi level here is close to the valence band. So we have a lot of electron. Okay, VTH is the VG, after which the inversion layer is formed. Okay, so why this is called inversion layer? Anyone has an idea?
Because now we have electrons for the channel instead of hole.
Very good. So now you have electron here, right? So this look like N, N, N. Isn't that we start with N, P, N? This is P substrate. I inverted the P to N. Of course, not everywhere. So maybe if I write this, it will confuse you. Right? Maybe I just write N on the top. Then you have a conducting region, right? I know you might learn this before, but I really want you to have this idea, right, before you graduate, of this picture, that how the transistor works. It can be reduced to some very simple concept. It is just to form the inversion layer. It's the inversion layer. Okay. And why this is important? Because later we need to calculate the capacitance. Right. So I'm sorry I spent many lectures to go over the basics, not because I'm a device guy. It's because if we want to understand the capacitance, we need to review all this device physics. Now you understand, after I form the inversion layer, I have a continuous channel here. Then what is the change of the capacitance between the gate and source drain? We will find out. Okay. Any questions? Now, so we talk about the threshold voltage, right? So once we increase the gate voltage and eventually we reach the threshold voltage, it is after which we start having the inversion layer. So at that point, right, this at the, it, right at this point, it finished the depletion process. It's not depleting anymore. Right? If you look at this band diagram, when I keep increasing the VG, this will go keep bending. So I have thicker and thicker depletion layer. Right? This is the depletion layer. I have thicker and thicker depletion layer. But eventually it will stop. Why it stop? Because it start having inversion layer. Then the electric field will not penetrate anymore. It will just keep forming more mobile electron. Okay, so that is the threshold voltage. Okay, finish the depletion process and only forms the inversion layer. And only the inversion layer is useful for the conduction. Mobile electron contribute to the current. Okay, so we keep doing, applying positive gate bias, but it's still not conducting, right? It keep increasing the depletion layer. But eventually, after the threshold voltage, it forms the inversion layer, then it can conduct current. Okay. Then we discuss so many concepts. Again, that is how I teach this class, right? Well, it's not device physics. Then we jump to the final equation. There's no need to derive this equation. What we want to know is what are the factors affecting the threshold voltage? That is, again, what is threshold voltage? Is the VG, after which you only form the inversion layer. You no longer deplete. You're doing something useful for the current conduction. Okay, so what are the factors that affect the VTH? I list out many things. That's what you just asked me. Find MS. This is the metal work function. Why is that? It's not a device physics class. I'm not going to explain, but you can see that it's affected by the Venn diagram. Okay, so the metal work function is affecting. Find F. This is related to the distance between the mid gap and the Fermi level, right? So this is related to the Fermi level in the substrate, which is related to the doping. And besides this, it also related to the depletion layer charge. In order to form the threshold voltage, I just told you that you need to deplete certain area of the silicon. And this depletion charge is going to contribute to the threshold voltage. It's going to be sustained by the VG, right? So it's Q over C. C is the gate oxide thickness. You may have some surface charge and some implantation, but all this, you just treat them as the additional charge. Just treat this as additional charge. That you do it deliberately or right? It can be defect. Okay, so you see that the threshold voltage depends on all these things, right? As a circuit designer, you don't need to calculate yourself. But if the foundry told you that, oh, I'm sorry, this time the VTH get a little bit higher because we make a mistake that we did an extra implant by our engineer, then you understand why, because you introduce new charge. Right? Or I told you that this time the variation is bigger because we have some big variation on the metal work function. Then you understand why. And because you understand why, you still can evaluate the results. You see, okay, my circuit performs like this and that. And that's because of the variation. If there were not variation based on this equation, I know that it probably will work. Then you can move in the right direction. But if you don't know, you just always know something is VTH, you don't know what is the background, it's difficult to talk to the foundry. And by the way, there is a position called foundry interface for all the fabless companies. And it's better you know about this. Okay, so this is threshold voltage. Now then, threshold voltage is great, but we also have something called body effect. I just told you earlier. We can bias the body to change the threshold voltage. And basically, this VT0 here, it is actually quoted here again. This is the same equation as the above one. If I try to have a reverse bias to the body, I can increase the threshold voltage. And this is very important for you guys in this class. Nowadays, all the chip, most of the chip, they use the so-called dynamic threshold voltage to save the energy. For example, if I want to save the energy, I can apply body bias so that the threshold voltage increase. And then, yeah, it's lower, but however, it saves a lot of energy. Okay, so how do we do this? Basically, it is like this. It's talking about something like this. Like this one you refer to here. I don't want you to get confused. Let's say you have a source, this is drain, and this is body, right? Let's draw the whole thing. That would be easier. I can apply source at 0 volt, but I can also apply body at -1 volt, or let's say 0.5 volt. Can you tell me when I apply body to -1 volt, is it a forward or reverse bias for this junction, PN junction between source and the body? Is this a forward or reverse bias?
Reverse bias.
Reverse.
Thank you very much. This is a reverse bias. And then, of course, this is forward bias. Now, why do I want to say this? This equation is very troublesome, especially when you start playing with the PMOS. All the signs just keep changing, and different textbook has different definition. For me, I don't like this. I use physics to help me. I remember that if it's reverse bias, it's going to increase the threshold voltage absolute value. When it is forward bias, it reduces the threshold voltage. This is not difficult to memorize. It's just forward bias, more current, right? So you reduce the threshold voltage. Although the current is not the same. Forward bias is talking about body to source current. But at the same time, it actually, but I try to relate to the current between source and drain, right? So memorize this. I bet you this will be very useful. By doing that, then I really don't need to check this equation so tediously. What is the definition of phi f? Is it positive or negative? Because it's going to affect my result. What is VSB? Okay, so if I do that, even for PMOS, I would rather think it in this way. VT equals to VT0 plus gamma times square root 2 phi f plus minus VSB minus square root 2 phi f. I put everything into positive, and if it is reverse bias, whether it's PMOS or NMOS, I use plus. If it is forward bias, whether it's NMOS or PMOS, I use minus. Because this is obviously is going to reduce my threshold voltage, right? So if you're talking about PMOS, maybe it's just -3 volt. I reverse bias it, then it becomes -3.1 volt. It increases the absolute value, make it more difficult to turn on. So you decide what to do. This is the way I memorize. And then I don't have to mess up with this plus minus, especially in the textbook, it has many different signs and different from other people's conventions sometimes. Okay, but the main point is here. You see that when VBS increase, more negative means it's reverse bias, right? Just now you told me that this is a NMOS, negative VBS negative is reverse bias, right? You do see the VTH keep increasing. Okay, I taught a lot, but does that make sense? It's just equation. You can do it, but understand the physics behind it and also have a good way to memorize. You pick a way that is good for you, right? If you understand the physics, you can memorize in this way, all the absolute value. If you don't understand, you need to play with this sign very carefully. Okay, so the main message in these 3 slides is, first of all, understand threshold voltage affected by many things. No problem. There's always Google, Wikipedia. You can find out what they are, but you need to put in the right value. Second is that the body effect. okay, is going to change the threshold voltage. Reverse bias is going to increase the absolute value. Forward bias is going to reduce. And here I show this figure. I forgot to mention, nowadays process is very complicated. In order to have different word function or different threshold voltage, nowadays for FinFET or SOI, this is SOI FinFET, they actually use the metal to tweak the word function instead of implant. So in order to do that, they have many different metal layers. You see this? For N-type, it has so many different steps. And then for P-type, you have another step. And then on the same wafer, you have different VTH. So you use different metal. Very complicated. Okay. Now then, let's go to the any questions so far? Everything all right? Let's go to the transistor equation, right? Then let's quickly just derive it. What is the current in a transistor? I, of course, is related to the width. Width is in this direction, right? We need to be very familiar with all these dimensions now. L is in this direction because we need to calculate the capacitance later. The total current, of course, is Q, just the induced charge, the inversion layer charge at a certain position times the velocity. This is the velocity. Okay. But what is the velocity? V equal to something called mu times E. Anyone tell me what is mu?
Electron mobility.
Thank you. Mobility, right? It's just saying that under certain electric field, how fast can you travel is proportional to something called mobility, right? And of course, we know this is just equal to mu dV dx. Now this becomes very confusing. Let me just take the, it can be, okay, let me write it better, okay? Right, and this one, let me write it really capital. This one is the potential. Right, you know that electric field is just dV dx. That's the, okay. And how about Qi? What is the charge that induced under the gate? May be confusing, but just go through what we have discussed. All the gate doing is to induce the charge under it through capacitive coupling. So isn't that this is nothing but just C times V? Correct? Charge equal to C times delta V. What is the C in our case? What is the capacitance in our case?
Oxide capacitance.
What do we call, say again?
Oxide capacitance.
Very good. It's just the oxide capacitance, right? This is the T-ox. And it is given here. And what is the delta V across this capacitance? What's the delta V? Then there is one V on one side is Vg. And then the other V on another side is Vx, right? Just the channel potential. Now, but I'm going to also subtract this by VTH because before VTH, it induces only depletion charge. We don't want to count it because it is not used for the transport. Depletion charge is not mobile. That's why I remove VTH. If I don't subtract VTH, the total charge induced is both the electron and also the depletion charge. Is this okay? Now, I just want to show you this, that's it, right? And then based on this one, Oh, sorry. Yeah. And then eventually, if you solve it, right, you even don't need to solve it if you like that. But why I show this, because I want you to at least know the background. Then you get I equal to W on L, right? This is the final result. Mu C ox divided times VGS minus VT times VDS minus VDS squared divided by 2. This is the equation you have learned in the so-called linear mode. Okay, but why we go through this? Because then you understand why the capacitance are important, right? Now, what if we go to so-called saturation? If we keep increasing the if we keep increasing the VD, right? Eventually, VGS minus Vx equal to L minus VTH is going to be equal to 0. Because I keep, this is L, right? This point is Vx equal to L at the end of the channel. Then it is equal to 0. But of course, this one is just equal to VD. Correct? Because that point touched the drain. Then there is Qi equal to 0, right? You cannot induce electron. Okay, and so that is the condition that when we GS minus VTH smaller or equal to VDS, right? This is the condition, right? From here to here. In this case, it goes into the saturation, okay? And then we say the current is just equal to W on L mu C ox divided by 2 VGS minus VT squared, right? I skip many things. I don't really try to discuss how I come up with this one. You can just substitute this one into the previous equation. There are lots of physics to discuss about. But you learned this already in your previous classes. The only thing you need to know, I want to remind you, is that have the concept. You understand that when it is saturation, there's no electron here. And why I want to do that, again, is related to the capacitance we're going to derive later. Right? So you cannot just say, I know saturation equation without understanding that you don't have any charge here. Right? So for this one, it's okay. You only remember this equation. But later, if you want to understand the capacitance we're going to derive, you need to understand that, yeah, because we have been saying that transistor is the gate controlling the channel resistance. It controlled by inducing inversion charge. But when the drain voltage is high, hey, I actually cannot induce charge here. It is fully depleted. And then we go into the saturation mode. Is this okay? Now, if this is okay, right? Then you might say that why I see the whole region is not has no electron. And that is true because if you keep increasing your VD, this is higher than the VG minus VT, then the certain point inside is also larger than VG minus VT. So your effective length is going to reduce. And that's why we have the so-called channel length modulation. Instead of just I equal to W on L, mu C ox divided by 2, VGS minus VT squared, your L is actually reducing, but we are not going to change it. We just use something called lambda, 1 plus lambda VDS to modulate this channel length modulation, CLM. So if I keep increasing IDS, my curve will still go up instead of flat out. Okay. Probably you know all this already, right? Now, so what will happen? This is what you learned before. linear equation when VDS minus is smaller than VGS minus VTH. We use this equation, right? This is in this region. And then when VDS, this is the curve, equal larger than VGS minus VT, then this is this region. For each curve, you have a certain VGS. Okay, any questions? This is just a review of what you learned before, but it's very important for us to move forward. This is the model, no old model, no problem, right? But now we want to ask, wait, what if my electric field is very high? What happened? We just now say that mobility, velocity equal to mobility times electric field. And this is so-called mu, isn't that? This is the velocity, and this is the electric field. This is the electric field. This is the velocity. But actually in silicon, if you keep increasing the electric field, you cannot indefinitely increase the velocity. This is not because of general relativity. It's just because when you activate the electron with higher energy, it increases the chance to lose more energy easily because of increasing mechanism of scattering. You want to know, it's like you enable it to do something called optical phonon scattering, which it cannot do when it has low energy. Okay, just like a person, right? You keep it growing up, you thought that it's earning more money, but then when that guy goes up, it has more spending, unlike a baby, which only eats and drink and sleep, right? So there is something called saturation velocity, the maximum that you can get to, okay? And there is an electric field. Once you reach there, you basically just traveling at saturation velocity. Okay, so what is the critical electric field? We say that at saturation velocity, right, your mobility is mu times E, right? So this is the critical electric field. So this is the point, it is what? 10 to the power 5, but I am going to multiply this by 100, so it becomes cm per second, divided by the mobility, 100 cm square V per s, which is 10 to the power 5 volt per cm. So once you reach this electric field, your electron will be traveling at a constant velocity, right? Even you add high electric field, it said refuse go to travel faster. That is the limit. So when will we hit this problem, velocity saturation? Think about 100 nanometer gate length. If assume everything is even, then what is the drain voltage divided by 100 nanometer will give you 10 to the power 5 volt per cm, right? If you do some math, 100 nanometer, I told you last time, is 10 to the power minus 9 meter, which is 10 to the power minus 7 centimeter times 10 to the power 5 volt per cm. What is this? 1 volt. So when you reach 100 nanometer, you go into velocity saturation regime already. So what is the conclusion of today's class? All you have learned are wrong, because I've been assuming constant velocity, mobility when I derive this equation. But now we are doing with very short channel, 100 nanometer or smaller. We need to consider the saturation velocity. Okay, so we will continue in the next class. Let me know if you have any questions.